Okay, so starting with empirical formula. So we have, usually you'll be given just percent compositions to start with. And so remember we have that rhyme to know the steps of doing an empirical formula problem that goes percent to mass, and then mass to mole, divide by small, multiply till whole. And so if you forget where to start, this rhyme's a good way to kind of maybe jog your memory a little bit. So we start by just taking our masses and rewriting them, or taking our percentages and rewriting them as masses. So I always make this in kind of a table format. And I'm going to move my camera a little bit closer because it's not super big right now. So I always like to table format, so I put my two elements. So I have carbon and I have sulfur. And then I'm just going to start, and I'm going to go ahead and convert my percentages into masses in this first kind of column here. So percent to mass, so carbon, I have 15.8%, so I'm going to put 15.8 grams of carbon, okay? Then I have 84.2% sulfur, so I'm going to put 84.2 grams of sulfur. So there's my mass. So I did my percent to mass step. Now I'm going to go mass to mole. And to convert mass to moles, remember we just used dimensional analysis, it's just a mole conversion. So grams of carbon goes on bottom, moles of carbon goes on top, and that'll get us into moles. And of course, to figure out how many grams are in 1 mole, we're going to look at our periodic table. And so carbon is 12.011, which usually it's safe, you can round it to 12, but I'm going to just keep it to be safe, 12.011 grams of carbon, and then I'll use my calculator in a second. I'm going to do the same thing for sulfur, grams of sulfur to moles of sulfur. And I know 1 mole of sulfur is equal to 32.066 grams. 32.066 grams. Okay, now I need a calculator, so let me find one. I didn't think that far ahead. Okay. Syntax error, that's always fun. Okay, so we have 15.8 divided by 12.011. And that gave me, oh, you see much better over here. You gave me 1.31546. And in these problems, I always like to keep a bunch of decimal places so I don't wind up with a rounding error. So this is my number of moles. And then I'm going to do the same thing for sulfur, 84.2 divided by 32.066. That gave me 2.6258 moles of sulfur. So we did our percent to mass, we did our mass to mole, next is divide by small. So we're looking for which number is the smaller number. And of course here the smaller is 1.31546. So I'm going to divide both these things by 1.31546. And when I do that, I get a value called the mole ratio. So up here, 1.31546 divided by itself is just going to be 1. And then 2.6258 divided by 1.31546 is going to be approximately 2. 1.996. And that is safe to just round that up to 2. So I don't need to multiply till whole because these are already whole numbers. So just multiply by 1, each of them by 1, so we end up with the same thing. We end up with 1 carbon and 2 sulfurs. So my empirical formula is CS2.
So if we don't have to multiply till whole, do you just leave it at 1? Like
Yep.
Multiply by 1?
Yep, just multiply by 1. So that last step, it can be multiplying by 1 to get to whole. So if we ended up with like 1.5 up here, then we'd have to multiply everything by 2 to get to whole numbers. No problem. Do you need anything else in that same regard, Achua?
I guess you might as well do, what's it, molecular mass.
What do you mean by that?
It's empirical, okay, molecular formula.
Molecular formula?
Yeah.
Okay, let me work out one real quick. Okay, so if it wanted you to find the molecular formula, it might say something like the molar mass. Oh, and I'm putting this under our next problem, so I'll cross that off for now. The molar mass of the molecule is 228.429 grams per mole. What is the molecular formula? Is that what you're talking about, Achua? Something like that? Okay. So if we're going to figure out what the molecular formula is, we need to first figure out the mass of our empirical formula. So step 1 is to figure out the mass of our empirical formula. So we have 1 carbon and 2 sulfurs. So our 1 carbon is going to have a mass of 12.011. Plus, we're going to have 2 times the mass of sulfur, 32.066. No. It would give you the molecular mass in the problem, and so it might tell you that it's 50. So the stuff that I'm about to underline would be the parts of the problem. So it would give you the percent by mass of your compound. So just like up here, and then it would say something like this: the molar mass of the molecule is this much. What is the molecular formula? So it would ask you to find both the empirical and the molecular formula. So and then sometimes it'll just give you the empirical formula and ask you to find the molecular formula. So maybe it would just give you the empirical formula is CS2. And the molar mass of this molecule is 228.429 grams per mole. What is the molecular formula? And so then you just want to start off by finding the mass of your empirical formula, which is what we're doing right now. So we have 32.066 times 2. Whoops, I did something weird in my calculator. Let's get rid of that. 6, so that plus 12.011, and that gave me 76.143. So what do you notice about the mass of the empirical formula? Is it more or less than the mass of our molecular formula? Yes. Yes, exactly. So we need, step 2 is to figure out how many times the empirical formula is the molecular formula. And to do that, we can divide the mass of the molecular formula by the mass of our empirical formula. So mass of molecular formula, which is given, divided by the mass of the empirical formula, which we just found. So we're going to do 228.429 grams divided by 76.143 grams. And so 228.429 divided by our previous answer gives us 3. So we know that our molecular formula is 3 times our empirical formula. So 3 times CS2 would give us C3S6. So that would be our molecular formula. Oh, I think I cut you off the page. Sorry, I didn't let you see the rest. Whoop, there we go. Can you see that now? Perfect. So, Ajwa, does that help answer your questions? Okay, perfect. So, first of all, when you're predicting products and whether or not a reaction will occur, remember that you want to have your solubility rules and you also want to have your activity series. And you can use both these on the test tomorrow. I will give you a copy to use on the test. So I'm just going to have these on hand so that we can use them when we need to. So this first one, what kind of reaction are we going to have in this first one with AgSO4 and NaNO3? Yeah, because we have two ionic compounds, so this is going to be double replacement. So remember, they're just going to switch partners. So the silver is going to bond with the nitrate, and the sodium is going to bond with the sulfate. So when you're predicting the products, you need to re-crisscross on the other side. And that's the most common mistake people make, is they just kind of like keep the same subscripts. So they just like throw Ag2, NO3 over there. And that's not actually right, because silver has +1 charge and nitrate has a -1 charge. So when they crisscross together, you get AgNO3. So we'll do that real quick. So let's start with that one. So Ag is going to cross with NO3. Okay, so silver has a +1 charge and nitrate has a -1 charge, so we just get Ag1, but we don't show that one, and then NO3. So there's our first reactant. I'm going to put a line next to it for us to balance later. Our first product. I said that completely wrong. And then our second product is going to be sodium bonding with sulfate. So let's recross those. Oh, I just threw my pen off the table. Just 1 second while I grab that. Let's see. All right, here we go. So we have sodium Na with a +1 charge, and then we have sulfate, SO4, with a 2- charge. So we get Na, and then this 2 crosses down, and then 1 SO4. And I'll put a line there so we can also balance that one. So we're so far so good on this? All right, cool. So now we need to balance. So anytime we have a reaction and we write products, once we figure out what our products are, then we balance the equation. We don't want to try, we can't just like choose to put the same number of each thing on each side. We have to first write the correct crisscrossed formulas, and then we can balance the equation. So now looking at this, we have 2 silvers on this side and only 1 over here. That's the very first thing I notice. So I'm going to fix that first by putting a 2 here. And that gives me 2 NO3s, so I know I'm going to have to also fix NO3 by putting a 2 here. And then I have 2 sodiums, so I look over here and there's 2 sodiums, so that's fixed, and then 1 sulfate and 1 sulfate. So now I think I'm balanced, so I'm going to fill in 1s everywhere else. Okay, so now we want to figure out whether or not this reaction occurs. So remember that double replacement have this weird set of rules for them to occur. So our reactants both have to be aqueous. AQ. So they both have to be soluble. So to check this, we want to check our solubility rules. So I'm going to do Ag2SO4 first. So I'm looking down my solubility rules, and the first rule that I see that applies to that is this compounds of SO4 rule. So compounds of SO4 generally do dissolve, and the exceptions are mercury, lead, strontium, and barium. So silver is no exception, so this will be aqueous. This will dissolve. This is soluble. So now let's check our second one. So sodium and sodium nitrate. So I'm looking at my rule. Sodium, right here, first rule, they generally dissolve, no exceptions, so this will also definitely dissolve. Okay, so now I'm moving to my product side. On our product side, either one needs to be insoluble, or one must be water, So there are 2 types of reactions. We have either a precipitation reaction where we get a solid, which is insoluble, or we have neutralization reactions where we have an acid and a base reacting together and one of our products is water. So when you did your limiting reactant lab, the type of reaction that you did was a neutralization reaction. So now we just have to look at our product side. We have silver nitrates. NO3 has no exceptions. This is going to be soluble, so it's going to be aqueous. And then Na2SO4, SO4 is also going to be soluble, and there are sodium is not an exception to that rule. And also you could look up here and say, okay, sodium is soluble, no exceptions. This one's also aqueous. So this reaction will not actually occur. This will be no reaction. So we can...
Those rules apply to all types of reactions, like single replacement, synthesis.
That is a great question. No, these rules only apply to double replacement. They're only for double replacement. For single replacement, the rules that apply are the activity series rules, which we can look at an example of that in a second. Sorry, I had to let my dog out real quick. So let's see. Let's find one that's a single replacement reaction. Okay, so number 6, this one with lead, Pb, and FeNO3. So lead is going to be replacing iron in here. And so lead, I am presuming, will have a +2 charge, but it doesn't actually tell us. So we're going to call this lead 2. Lead 2. So let's look at that one real quick, because then we can look at activity series and determining whether or not something will react. So, lead is a metal, so it's a cation, it's positively charged, so it can only replace another cation. So out of iron and nitrate, the cation, the other metal, is iron. So lead's going to try and kick out iron. So if lead succeeds in booting iron out, then iron's going to be by itself, so that'll be our first product. Iron by itself. And then our other product is going to be lead 2, so Pb with a +2 charge, crisscrossed with NO3. And NO3, of course, has a -1 charge. So when we crisscross that, we get Pb, and then NO3 is in parentheses because we have 2 of those, so the 2 goes outside the parentheses. And I'll put my line for balance.
Why exactly does Pb have a +2 charge?
That's just the most common charge of lead, but I would not expect you to know that. If it gave you one on the test, it would say Pb and then the 2 in parentheses, so it would tell you which charge to use. Yeah, so I just came up with one here. I just used the most common one because I don't really know what they're intending on this sheet. So, but yeah, it would be given to you. It would say Pb2, so you would know that lead should have a +2 charge over here. Okay, so now let's balance. So we have 2 nitrates over here, and we have 3 over here. So we have an odd number, so we're going to have to go ahead and make this an even number. To do that, we can put a 2 in front of this. So now we have 6 nitrates, so we can put a 3 over here to make 6 nitrates on the other side. And then we have 2 Fe's, so we're going to put 2 here, and 3 lead, so we'll put a 3 there. So that one's a little tricky to balance, but hopefully, just by some trial and error, you can get it balanced correctly. Okay, so then we want to determine whether or not this reaction really will happen. And so it has nothing to do with our solubility rules. We don't need to use this at all. What we do need to use is our activity series. And for our reaction to happen, for a single replacement reaction to happen, we need the lone element to be higher than what it is replacing. So
that will apply to both synthesis and decomposition as long as it's not double replacement.
So this only applies to single replacement. Synthesis, decomposition, and combustion, they will always occur. So you can assume that they will always happen.
Except with the exception of whether if it's just like a simple synthesis decomposition problem, that would always happen.
These will always happen. Yes, so single and double, the replacement reactions have those specific requirements for them to happen, but synthesis, decomposition, and combustion will always happen. That's correct. Okay, so for this one, just to finish it up, we need lead to be more reactive, so to be higher up than iron. So looking at our activity series, we have lead here, and we have iron up here, so lead is less reactive than iron. So this will not occur either. We won't get a reaction here because lead is not more reactive than iron. Does that make sense?
Yes.
Okay, perfect. Good. Okay, cool. All right, see you tomorrow. You too.